webinar, and it will be made available on our website when we finished. Just briefly about a quick overview of the NFM research programme. It's a 4-year, £4 million programme. We're carrying out novel science to improve understanding of natural flood management where possible, including quantification. We're looking at a range of NFM measures in different types of catchments, flooding scenarios, and at different scales. And the aim is to improve evidence and understanding for policymakers and practitioners. Now, a really key part of the success of our research programme is collaboration and working with partners. And we have really have got a large number of organisations and people that we're working with. And today is an example of that. So Andrea's not actually working as part of the research programme, but we're keen to build a community of people working in NFM and related research. So we're really pleased that Andrea could join us today. So Andrea is a research fellow in water resource systems modelling at Cranfield University. So Andrea, I'll hand over to you now.
Okay, thank you very much, Gerard. I'm going to switch to my presentation now. I hope everyone can see it. Well, thank you, Gerard, as I said, and thanks to the Natural Flood Management Programme for inviting me to present today. So as part of these collaborations or interactions between the program and other related research, I'm going to talk about how cover crops can be used as a land management measure, but not specifically for flood management purposes, although it's everything is related, and I will highlight that at the end of my presentation. So I also want to acknowledge Miyo Yoshizaki, that is the student that developed this study during the MSc thesis that she did as part of the environmental water management course here at Cranfield. That was supervised by myself, Sarah de Baetz from another institute focused on soil and agri-food, and from the Water Science Institute, and also Sean Dowman from Affinity Water, specifically from the catchment management team. Well, I didn't mention it, but the study was supported by Affinity Water itself, that sponsored the study and provided the case study and the data and part of the data for developing it, and is also related to a larger project funded by BBSRC that is called Using Roots to Bioengineer Soil, that is led by Sarah de Baetz here at Cranfield. So now, yes, moving on into the background or how this study is framed. It is a fact that a very significant fraction of land is used for agricultural purposes. For example, in England, it represents 70% of the land we use. So this use of land for agriculture will likely increase in the future as population grows. So we know that intensive agricultural practices cause problems such as compaction and tillage that are related to issues such as increased erosion or reduced infiltration that leads to water scarcity and more risk of floods. And those pose serious problems for catchment managers nowadays. As you may know, they are responsible not only of providing, so water companies are responsible not only of providing water for drinking to the different urban areas, but they are also responsible of managing the catchment that provides all those water resources in quality and quantity. So in this presentation, I will focus on cover crops as one of the options to mitigate those problems mentioned: loss of infiltration capacity, increased erosion, basically. Or probably most of you know, but the cover crops application is an agricultural practice in which the land that is fallow for a certain period of time is planted with a secondary crop that is not a commercial crop. and so it's not harvestable. For example, oat, rye, or mustard, some varieties of those. They are really convenient as they don't represent or they don't require big changes in the agricultural management, so they fit very well into existing farming practices. And also have wider benefits such as restoring plant diversity and enhancing, retaining nutrients and increasing the water holding capacity of soil. So they have clear benefits for farmers. And many studies have highlighted those benefits in terms of food production or increase of agricultural production. However, implementing cover crops involves additional costs, for example, for seeds, and also involves additional work to grow and harvest the crops. That makes some farmers reluctant to use them. So then the issue is water companies or catchment managers, that is the same in the UK, are responsible for managing those catchments, and they believe that cover crops can have benefits beyond the farm scale, and so they can have benefits at the catchment scale for the water broader contexts. But they are lacking studies that define and quantify how significant those impacts are, those benefits are. So water companies need evidence to decide whether it's worth to get those benefits of increased infiltration, decreased runoff and erosion. If it is worth maybe negotiating or even investing in payment schemes with farmers to get those benefits on increased water quality and water quantity in their water resources. So as to try to achieve that these types of measures are extensively applied in their catchments. There is also a need to understand what will be the effectiveness of cover crops under more intense rainfall events that we foresee in the UK under climate change. So this is the context and the background that frames the aims and objectives of this study, that aims at estimating or evaluating the effectiveness of different cover crop mixes on two hydrological processes that drive the problems or the issues that I mentioned before, such as infiltration and erosion, soil erosion at catchment scale under current and future conditions. So that will be done in two different steps. First, conducting laboratory controlled trials that give us the detailed understanding of the processes and how the cover crop mixes influence the behavior of those hydrological processes, and then using these experimental results to set up catchment scale models that give us an estimation of what are the benefits in infiltration and erosion at a larger scale that is meaningful and relevant for the catchment managers, the water companies. So as I said, Affinity Water was behind this study. It was them who raised this issue as one of the main challenges that they were facing in their catchments, and they offered the Lea catchment in Hertfordshire as the case study area. It is a catchment around 200 square kilometers. As I said, is managed by Affinity Water, and they have a cover crop scheme in place in which approximately 25% of the cover of the scheme area is applying at the moment cover crops in the fallow period that in this specific agricultural area goes from August to January. So it's winter cover crops. So you can see in the figure that the cover crop scheme is marked in the red line with the red boundary. And we also, of course, needed to characterize what were the physical conditions of the catchment in terms of soil, land cover, slope, etc. As you can see from the legend in the figure, the brown color corresponds to farmland and is the main land use in the study area. The blue boundaries represent the hydrological boundaries, the subcatchments that overlapped with the cover crop scheme area and correspond to the two subcatchments of the River Lea. I will also relate these two catchments to the river flow data that we had for calibration, that we used for calibration. Well, I think it's important to mention as well that the cover crop scheme has been in place for about 4 to 5 years now, so it's quite recent in time, although they already have some experience on the implementation of cover crop schemes in farmland. Okay, so this leads us to the methodological approach that we took for the study, although I briefly named that we had 2 stages. So the first one, or the first part of what information we were obtaining from the different stages, we conducted laboratory controlled experiments that we coupled somehow with catchment scale modeling. From the laboratory experiments, repeating a little bit myself, we obtained a detailed understanding of what was the effect, the benefit of specific cover crop mixes on infiltration and concentrated flow erosion. While from the catchment modeling side, we wanted to understand the large scale behavior of infiltration and erosion processes. But then we had to couple these two somehow. So what we did was, after selecting the catchment models and performing the experiments, we assimilated or find the correspondences between the parameters in the models and the experimental data that we had in order to represent different scenarios for different cover crop coverages in the catchment. So, as I said, we defined different cover crop coverages, different scenarios, and also because we wanted to understand the impact on the current and future conditions, we also defined different climate change scenarios. With that, we were able to assess the effects of cover crops. So we achieved our aim of understanding the effect of cover crops at the catchment scale now and under climate change. To develop this work, we used different facilities that we have at Cranfield. So we have a huge greenhouse that it's a partnership between the Crop Health Protection Association and Cranfield. That greenhouse allows to grow different crops with controlled day length time. It has multiple sensors to monitor biomass growth, temperature, etc. And it also has irrigation control, measuring the weight evolution of the different plots in which the crops are growing. So it's a quite high-tech facility that we have at Cranfield and that we used specifically in our study to grow the plots that we used for the infiltration experiments. We also have other facilities, the plant growth facilities, that are growth rooms in which the temperature, humidity, day length, etc. are much more controlled than in a greenhouse, of course, because the greenhouse at the end, it's a little bit less difficult to have under strict variables, to maintain strict variables there. But the plant growth facilities allowed us to really represent the growing conditions that we wanted for our cover crops that were supposed to be growing during the fallow period, that period that we mentioned from August till January, but we only considered the 2 first months of growth in which we consider that the cover crops have had enough time to develop their roots and their above ground systems well enough to start having or providing benefits. We also have a pilot home on the water theme in which we had We have different devices, such as, for example, an erosion plume that we used for the erosion experiments. So I already gave a glimpse of it, but we used two different types of plots or samples for the infiltration experiments and the erosion experiments, because they required different levels of development or to really show the benefits. So for the infiltration experiments, we had larger plots grown in a 1 per 1 meter wide boxes with almost 1 meter depth. While for the erosion experiments, because the boxes had to fit in the erosion plume, we had to go for a much smaller plot that was 30 centimeters side and 30 centimeters wide. So one note here is that actually the erosion plume only allowed 10 centimeters depth for the boxes, but we wanted the roots to grow really as much as possible. So we put two boxes, one of 20 centimeters, and on top of that, another one with a perforated bottom of 10 centimeters. So we allow the crops to grow for a little bit more than 2 months in this 30 centimeters deep box. And then at the time of running the experiments, we removed the 20 centimeters box from the bottom, and then we could use the 30 by 30 by 10 to fit it in the erosion plume. So those are technical things that when you are doing experimental work, you have to figure out in order to have your samples, the samples you want, but also that they match the instrumentation you have. We also selected the soil that was aligned with the soil we could find in the field. We defined the bulk density so that they were comparable as much as we could, because those variables sometimes are a bit difficult to control. As I said, the infiltration plots were growth in a glass house under somehow controlled environment, at least the length of the day. And then the erosion experiments were, the plots for the erosion experiments were done in the growth rooms with a very, very strict control of the conditions of temperature, relative humidity, and light intensity and duration over time. So in relation to the type of cover crop mixes that we used 3 different cover crop mixes: oat and mustard, and phacelia, and rye, mustard, and phacelia. Selection of these cover crop mixes was based on previous studies. As I mentioned at the beginning, this project was aligned with a larger one, using roots to bioengineer soil. And in an initial phase or a previous phase of that project, they tested the properties and the effectiveness of the different individual cover crops. And then from the main findings of those studies, we decided to test these cover crop mixes because of the complementary properties or benefits that they brought. So we defined our seeding density, and although we growth more than 3 replicates for time constraint reasons and for some problems growing the crops, at the end we were able only to use 3 replicates of each cover crop mix, and also for the bare soil. So going into the details about the individual experiments that we performed in the laboratory, the infiltration experiments were done using a mini disc infiltrometer, in which we had to define the suction that we wanted to use for the experiments. That depends on the type of soil that you have. And what we wanted to estimate with that was the unsaturated hydraulic conductivity of the different soils. So we did, for the 3 different replicates of the 3 different cover crop mixes, 3 measurements in each. So at the end we have 9 measurements for each cover crop mix. And we measured the infiltrated water volume every 30 seconds. We recorded that. So with the equations that I'm not going to go through, but we adjusted a curve of the infiltration rate, and from that we were able to calculate the unsaturated hydraulic conductivity. There was also, we also scanned the roots and analyzed the development of the roots and the main features in terms of density, whether they were thinner or thicker, more straight or more entangled, let's say. The second set of tests that we did related to the erosion, the soil erosion by concentrated, due to concentrated flow. For that, we used a sediment erosion plume that was here in the pilot hall at Cranfield. In this case, we measured different variables, many different variables, water depth, upstream, in the middle of the sample, downstream, turbidity, sediment load, and also the plant features, how much was the above ground biomass, the stem density, the thickness, the height, etc. And we also scanned the roots and analyzed the underground biomass features. Because we wanted to explore the behavior of the cover crop and the soil under current and different and future climate change conditions, we tested each sample under different flow conditions ranging from 0.5 to 11 liters per second that we increased every 1.5 minutes. So what we did was we set the discharge, let it for 30 seconds to stabilize, and then we measured all the variables, keeping that discharge stable for 1 minute. Then we increased to the second discharge level. We left it for 30 seconds to stabilize, and then subsequently until we reached the maximum flow of the range. And all the variables that we measured allowed us to calculate the shear stress, the flow velocity, and also the absolute soil detachment, from which we could obtain the soil erodibility coefficient. That is the K that is in the equation, in the last equation to the right. So just to give you an overview of the results that we obtained based on the plant features. Well, here, actually, this is just a summary to clarify, or so that you can clearly see what are the differences between the different individual crops that we tested. So we have oat that has quite long and thin and very dense root structure. Then we have mustard that has thicker and straighter roots, and especially it loses a lot of density towards the bottom. Then Phacelia, it has the thickness is in between mustard and oat and has much less density. And then rye is similar to oat, but the roots are less thin. But we didn't test each of them individually. So we mixed, we performed mixes. And in that regard, we could see that when they were grown together in the same plot, oat, mustard, Phacelia mix developed their roots relatively better than the other two mixes. So while oat mustard and rye mustard Phacelia developed relatively thick and straight roots in the deepest part of the boxes, they didn't have so many roots in the top part. And on the contrary, oat mustard Phacelia developed a mixture of thick, straight, and thin branched roots, both in the top and the bottom parts of the profile that we analyzed. In relation to the above ground biomass, we can see from the results that the stem diameters in mustard are much larger, giving them, making them more stiff, while the ones that are more flexible or thinner is oat. And this is something that will determine the behavior afterwards in the results of the experiments. So these are the first results of the tests for infiltration that provided unsaturated conductivity. And we can see that compared to bare soil, the one that improves the infiltration more is oat mustard facilia mix, potentially because it has a higher root density, as we mentioned, that continuous mix of root of thick and straight and branched and thin roots on the whole profile of the soil. And although I am not showing the results here because that is not a direct result from this study, but they appeared to be better than the individual crops, oat, mustard, and facilia separately. And these didn't happen with the other two cover crop mixes. There weren't significant differences between the individual species and the mix in the other two mixes. Only for oat, mustard, and facilia, we could see an enhancement of the mix with respect to the individual. So there were kind of synergies between the different species of cover crop. As regards to the erosion, in which what we could observe, if you look at the graph on the right, what we can see is the absolute soil detachment represented against the shear stress. The critical shear stress that represents the shear stress at which the soil particles start mobilizing. Okay, that shear stress increases significantly in all the three cover crop mixes, meaning that they are able to retain soil for higher or better under higher flow conditions that create a higher shear stress. And we also can see the slope of the linear regression, that is the concentrated flow soil erodibility. And we can see that the one on the left is with the dark triangles, the black triangles, is the bare soil condition, is the one that has the steepest slope, meaning that, that there is higher soil detachment as the shear stress or the flow increases. While with all the three cover crop mixes, we managed to reduce the soil erodibility. And again, the one that has the best results is the oat mustard facilia. So for the unsaturated hydraulic conductivity, we only looked at the roots because that is the component of the cover crop that will have an impact on this hydrological property. But for the erosion, the above ground biomass also has an impact on how the process occurs. So in this regard, we observed that the thicker stems of mustard that we just mentioned, that they were thicker and stiffer, provide a higher resistance to the flow, so they manage to slow down flow. However, they also create more turbulence around those stems. And this is where the couple mustard and oat could play a synergistic role, because the more flexible above ground biomass of oat would somehow break that turbulence and reduce the drag of flow on the soil particles. And therefore, we observed, or we concluded, that the mixture of rigid and flexible plant stems would maximize the advantages and would be synergistic in preventing soil erosion. In relation to the root system for preventing erosion and increasing potentially that shear stress, previous studies demonstrated a negative relationship between root density and soil detachment. So that very dense and fine mesh of roots that the oat mustard facilia provides would be potentially beneficial to increase the critical shear stress and reduce soil erodibility. Okay, so now moving on to, so we finished the experiments, and these are the main conclusions that we identify from the detailed understanding of the processes and how the different species and mixes benefited the different processes that we were trying to understand. Then we had to go to the second stage that was trying to model the processes at catchment scale. So for that, in this case, and because it was an MSc thesis and we had a little bit of time constraints, we went to quite simple or non-process based models. So we used conceptual models like the TEMET model that allows us to represent different flow components. So we have runoff, we have infiltration, we have groundwater or base flow discharge, etc. So we set it up at a daily time step using data from the National River Flow Archive, and we used the land cover and the potential evapotranspiration from the Center for Ecology and Hydrology. And the parameters that we should define were Hmax, that gives us more or less an estimation of the soil capacity or the soil water content, the maximum soil water content of the soil. Imax was the maximum infiltration of that soil. It is a coefficient that defines the runoff threshold based on soil water content and Hmax. And then alpha is the discharge parameter in the linear reservoir. That is how this specific TEMET model considers the aquifer. So for the parameterization, we used observed flows in two gauging stations, the one at the outlet of the two subbasins that I showed in the map of the case study from the National River Flow Archive, and we used two different subsets of data for calibration and validation that were quantified with the Pearson correlation coefficient. Again, we used quite a conceptual or simple model to represent the concentrated flow erosion as a combination of sheet and real erosion. I suppose you all more or less know the universal soil loss equation, but it basically considers the effect of rainfall intensity on the erosivity, on the erosion process, on splash soil detachment. Then it also takes into account the characteristics of the soil itself and what is the slope, the length and slope in which that erosion process occurs. It also has consideration of what is the land cover in place, and then support practice factors that show if there is a good maintenance of that soil, or there is a lot of soil alteration in the management. So for the parameterization, we basically took the values of most of the variables from the European Soil Data Center that has done an application of the universal soil loss equation over all Europe. And then for the parameters that weren't available, we used values of 1 for the practice factor because we didn't have data, and we considered that our soil was bare under the baseline conditions, because as I said, we are using data, we are considering a quite long period from 1990 to 2015, while the cover crop scheme in the area was only in the last 4 or 5 years. So we can assume that there was that the soil is bare in the period in which we are analyzing the erosion process, that is only during the follow months from August till January. And because we didn't have soil sediment low data or suspended sediment data in the outlets of the catchment, we evaluated the results of the model based on general literature data for soil loss in cultivated land in the UK in similar regions. Just to give you a short overview of how the models performed. You can see above the results of the TMF model in the two different outlets of the subcatchments. Visually, you can see that they adjusted pretty well in the calibration and validation, and also the Pearson's correlation, although it is not a very demanding performance indicator, but they are good to excellent results in calibration. And as regards to the erosion model, our results provided around 3 tons per hectare in the fallow period that covers 6 months of the year. And comparing that to literature reviews or literature values in cultivated land in the UK, the value for 1 year would be around 6, so we are in the range, and then we consider that at least for the purpose of comparing baseline and future scenarios, the model was suitable. Okay, I'm going to speed up because I'm speaking a lot and I'm running out of time. So the next step then was assimilating or trying to find that relationship between the cover crop effects or the detailed processes into the model parameters. So we decided to reflect the infiltration effectiveness of cover crops in the parameter IMAX of the TMF model. We considered that the calibrated value corresponded to bare soil, so 0% application of cover crops in the baseline, as I mentioned. And what we did, we used the variability of the unsaturated soil conductivity, hydraulic conductivity in the soil, the variability observed in the experiments, to capture the overall trends of the IMAX parameter. So this is the variability between bare and crop soil and the cover crop, and then applying a correction factor for the area in which the cover crop would be applied in different scenarios, different cover crop coverage scenarios. And for the erosion process, we considered that the cover crop factor in the universal soil loss equation would be representing the effect of the cover crops. And so what we used to transfer the effect of the cover crop from the bare into the application of the measure is the concentrated flow soil erosivity. So these are the scenarios that we run. We run different scenarios for the 3 different cover crop mixes under different cover crop coverages. 25, that is the current cover crop scheme. It's like, okay, if what we have started or what is in place now continues over time, that 25% coverage or application of cover crops in arable land, or if we increase it up to 100%, all arable land in this cover crop scheme is under cover crop winter cover crops. And then we tested that in the current under current climate conditions, basically precipitation and the future rainfall projections. In that regard, we considered the projections for RCP 4.5, that is an intermediate emission scenario, under mid and end century projections. And what, in summary, those projections point to a decrease in 55% in summer rainfall and an increase in around 35% in winter rainfall. So, an overview of the results at catchment scale and comparing the different scenarios, we can see again and align with the experimental results as it's kind of obvious. The largest improvements occurred under oat master facilia mix. We can see that infiltration, so that in general all cover crop mixes improve infiltration with respect to the baseline. This is the graph above, gives us the effectiveness on recharge as a percentage with respect to the baseline. But the benefit increases in the future scenario. So we have a much larger enhancement of recharge under more intense rainfall events. As we can see, for example, in the Oatmaster Facilia in the feature in the top graph that reaches values above 25% increase in recharge with respect to the baseline. Also, we can see that in the bottom graph that referred to the erosion over the fallow period, we see that it is enhanced, or its impacts are better under future conditions. Sorry. And again, we can see that the reduction in, here we are representing the erosion, so the total soil detachment for the different mixes and over the different climate conditions. And we can see that the reduction in absolute soil detachment is much larger in the Oatmaster Facilia in the future conditions. Just to wrap up a little bit, and I'm very happy because I'm just on time, recognizing the limitations of our study and what can be developed in further research to get a better insight or expand the present study, we could, for example, run more experiments to get more replicates so that the significance of the results that we get, the behavior of different species is more robust. We could use better or more process-based models to represent the behavior of those hydrological processes at catchment scale and have a more direct relationship between the experimental results and the modeling results. And also, if we tested 25% coverage and 100% coverage, but if we linked that into a cost-benefit analysis on how much is the investment of implementing the cover crops and what are the benefits in economic terms, we could identify potentially the optimal cover crop coverage. So linking this to the flood mitigation, that is the topic of this of the natural flood management program, there are other benefits to using cover crops, and one of them, and I'm sure the audience knows, is flood mitigation. We have seen that cover crops increase infiltration and they have potential to decrease flow velocity, resulting in potentially flood abatement. However, the time scales of the process that we have tested here that are more continuous, long-term hydrological processes rather than event-based processes are different, and then that would require, analyzing the benefits of cover crops in flood mitigation would require more experiments to test the response under extreme events and also under saturated conditions. There are also other benefits that cover crops bring, such as pollution control, soil structure improvement, biodiversity enhancement, and there is research ongoing in relation to that. So I think that overall, if we link all together, that can be a very interesting measure for our catchments to have a more sustainable management of our catchments. And that's what I wanted to say. Thank you very much, and I'm open to your questions or comments.
Great, thanks very much, Andrea. Very interesting. Can you see the chat function? There's Ian's made a couple of points and asked. He's got some local knowledge.
Yeah, yes. So someone is asking, your work looks to be assessing a very simplified model of cover crop influence in soil infiltration. The major driving factors in infiltration are soil, organic content, and bog density. These change significantly over time where repeated. Does your project account for this? Well, as I recognized now at the end, we know that the type of models that we used are too simplistic, so they are not process-based models, and they do not account for many of the variables that we know drive the processes. And therefore, yes, I agree with you. This is something that that should be explored further, and I think it's worth it. but unfortunately we didn't have time or resources to go for that more detailed modeling. And yes, the second question goes specifically asks about the local variability in the soil in the Lea catchment and whether this affects the reliability of our model conclusions. Well, of course it does. Well, although we didn't analyze the whole Lea catchment and the variability in our study area is not as large as it is in the whole catchment, but yes, it does. And having a more detailed mapping of the soil characteristics and having a more process-based model to represent or to be sensitive to those changing characteristics. I didn't mention it, but we applied the models, specifically the surface runoff model, lumped into, well, semi-lumped into the two subcatchments. So using a more distributed approach to the modeling as well, we could account for these variabilities. However, in terms of the experimental work, it is really difficult and challenging to grow the crops and test them for all the range of soils. So that should be also, there would be a lot of uncertainty in how to extrapolate the results of the experiments for a specific type of soil into the different soils in the catchment. So that would be something challenging to approach if we had a model that was sensitive to those changes. And someone posted another one.
Is another Ian? Yep.
So what outcomes were you looking for, and what advice are you hoping to give to landowners, etc.? Are you looking to give a value on cover crop use that funding streams know how much there is worth per hectare? Well, as I said, our study didn't look into that, but I think in terms of convincing or providing evidence to both farmers and catchment managers or water companies that it is worth investing for multiple reasons on cover crops, it is interesting to provide an economic value on that, although it's a little bit challenging. Some of them are easier to estimate, but for example, the increase in productivity that is due to many in agricultural productivity, that is due to many other factors, such as what is the weather or the weather in that growing season, or many factors. It is difficult to detach what is the added value specifically of cover crops. But for example, other values, such as what is the reduction in soil in water treatment due to enhanced water quality, those are things that we have done also here at Cranfield with some other studies. And so yeah, it would be valuable to have at least a range of economic benefits in mind to put on the table and enable farmers and catchment managers to negotiate and find an agreement to use this tool that cover crops represent.
Thank you. We received a number of questions beforehand. Were there any of those that you'd like to pick up on, or would you like me to pick them out? You feel I don't know
if I'm skipping some, but I just saw one, the last one that arrived, that said you are showing big influence on cover cropping for the hydrological cycle.
Oh, sorry, the questions that people submitted beforehand.
Okay, yeah. If you can, I don't have the
okay.
that you sent me. So
yeah, okay. Well, there was a question about how the extent to which cover crops can help to protect raw water sources nearby or on the same land, and some consideration of pesticide management plans near such raw water resources. Do you have any comments on that?
Well, we haven't done any study on that. I know that cover crops are being explored specifically by affinity water also in terms of nutrient retention in the soil, so avoiding them being mobilized with runoff into the rivers. Not so much specifically on pesticides, on pesticide pollution, but as we have seen here, so cover crops somehow disrupt the flow and have the potential to slow it down somehow, facilitating or preventing that it is mobilized so easily or facilitating deposition. So they could be potentially useful, but it's something that I haven't explored in detail. So I cannot give, I don't know, a very
Okay, yeah.
answer.
Another one which I think is talking about next steps. The person asked if you'd got any ideas about catchment scale trials or demonstrations to encourage water companies to fund cover crops. I know you've had funding from Affinity Water, but yes, is that likely? What are the next steps likely to be? Do you know? Or what would you recommend?
Well, apart from probably using more sophisticated catchment scale models to represent the processes, a good option would be validating those afterwards somehow in the field. Although, yeah, depending on the size of the catchment, it can be a little bit challenging in terms of resources. But monitoring the key variables of the hydrological process at the catchment scale, and then comparing to validate that the assumptions and that translation or assimilation of the experimental results into the models are valid, that would be really interesting. And I think it would give more confidence that we can move forward with the modeling work. So somehow ground validation of those models would be a very interesting option.
Okay. On a more practical level, somebody asked about the machinery requirements for cover cropping, including undersowing. Can you do you know anything about that?
I'm afraid I'm not very familiar with farming techniques.
If anybody else who's listening can offer advice on that, then please say something in the chat. And then I think you covered this to some extent, but there was a question about on the tangible and financial benefits of cover crops.
Someone here in the chat has pointed out that the Lea catchment, there are 3 small subcatchments that are flow gauged and could be targeted to validate the idea at field scale. So this is in like following up the ground-based validation that I just mentioned.
Okay.
But yeah, there are other questions.
Well, yeah, I was just asked about the financial benefits of cover crops. Could you say any more about that?
Well, I think I already.
Yes. Okay. Yeah, I think you covered it.
Yeah. So given that Affinity are predicting a shortage of supply by 2030 of 26 megaliters per day, there should be a clear case for funding cover cropping as a public good. Yeah, I mean, as I said, Affinity are working in this line, and of course, it's not me who has to talk about their strategies to go ahead and solve their challenges, but that is why they get engaged with this type of studies, because they really want to have evidence to back the investment decisions that they make, and to guide a little bit their decisions around catchment management. But yeah, so in light of the results, I would say that the results have encouraged them to move or to continue in the line that they were doing with the cover crop schemes. So yeah, that's a positive thing. That's a nice result from the partnership that we had for this study.
Yeah, it's good to see some people commenting on the chat. One other question that was submitted beforehand was how quickly can appropriate management techniques improve water infiltration rates in long-term arable soils?
Well, so I suppose that that depends on the baseline situation. So what is the starting point? What is the status of the soil? What is the depth of the issues in terms of soil compaction and etc. But as we showed in the and we were using a bulk density that was representative of an average farming land. So considering that machinery has been used, etc. And so it has increased soil compaction at the bottom part and a little bit looser soil on the top part. So, and we saw that after only 2 months growth, they were already significant benefits or benefits that at least we could observe. So if you let the cover crop keep growing and develop the roots, I think that the benefits will increase over time. So what from the findings of our study, I would say that on an average farming landfill that is not the worst management, that hasn't suffered the worst management practices possible, they should be effective during the first season in which they are implemented. But yeah, I cannot of course extrapolate that to all arable land, because there is a lot of variability on, as you were saying, the history that land has gone through. So
Okay, thanks, Andrea. I think we'd better bring it to a close now. Just somebody did send a question about flood management in catchments in the Himalayan region, which Andrea and I briefly talked about before. So just to say, if anyone's got expertise in that, do get in touch, and we'll put you in touch with the person that asked that question. So yeah, just to conclude then. If you've got any feedback on the presentation, any follow-up questions, any comments on how it went technically, please do let us know. The recording will be available on our website if you go to the webinars page on our website. And also, Andrea, is it okay to make your slides available?
yes, well, I will discuss it with the sponsors, but I suppose that should
okay.
be fine, so, yeah.
If we can, we will.
Yes.
The next webinar is on the 17th of February. It's Dr. Ian Pattison from Heriot-Watt University, and he'll be talking about the role of land management in mitigating catchment flood risk. I'll post a link to allow you to book for that on the website in the next few days. And if you're subscribed to our newsletter, a little plug for that, you'll receive an invitation to join that webinar. And yes, you can sign up for the newsletter on our website as well. You can unsubscribe as well, so you're not signing up for life. Great, that's all we've got time for. So thanks again for joining us, and thanks in particular to Andrea for a very interesting, informative presentation.
Thanks to you for listening.
Thanks, everyone. Goodbye. Bye.